Something happened in China in 2025 that caught the world completely off guard. A factory there began producing a new type of battery that doesn't use lithium at all. Instead, it relies on an incredibly common material, something you may already have sitting in your kitchen. This ordinary material costs around $1 per pound, yet it can be used to make batteries that are safer, perform better in extreme cold, and may last for decades of daily charging. Even more surprising, the company behind the technology reportedly secured a massive battery order worth around 60 gigawatt-hours. To put that into perspective, the deal represents a huge portion of the company's total battery production across all of 2025. Meanwhile, American battery companies had spent decades heavily investing in lithium. Alternative technologies were available, but many were dismissed as experimental or impractical. Now, that decision may be coming back to haunt the industry. If you enjoy stories about technology, energy, and major breakthroughs, make sure to like this video and subscribe for more. Because this is the story of how China began exploring a path beyond lithium, while much of the world was still focused on improving it. But to understand why this matters, we first need to understand how lithium became the king of batteries. How lithium took over. Go back to the early 1990s. Phones were bulky, laptops were heavy, and portable video cameras could barely run for an hour. The idea of having a powerful computer in your pocket that could last all day seemed almost impossible. The biggest problem was energy density. Engineers needed to store more energy in smaller and lighter batteries. Then, in 1991, Sony introduced the first commercially available lithium-ion battery. The change was dramatic. Lithium-ion technology could store far more energy without adding excessive weight. Suddenly, electronic devices could become smaller, lighter, and more powerful. That technology helped transform almost everything around us, from smartphones and laptops to wireless earbuds, cordless tools, and eventually electric vehicles. So why was lithium so effective? The answer is simple. Lithium is extremely lightweight, which makes it ideal for portable devices. At the same time, lithium-based chemistry can deliver high voltage and significant amounts of energy. Lightweight plus powerful was the perfect combination. For the next 30 years, the world went all in on lithium. Billions of dollars were invested in lithium mining and battery manufacturing. Countries such as Australia and Chile became major suppliers. Factories grew larger, production became more efficient, and battery prices continued to fall. Electric cars could travel farther. Phones became thinner. Laptops became lighter. Lithium appeared to be the answer to almost every battery problem. But there was a hidden weakness in this success. When an industry finds a technology that works extremely well, it can become difficult to convince people to search for something completely different. Lithium became the industry standard. Investors trusted it. Manufacturers built massive factories around it. Engineers spent years improving it. So the question became, why change something that already works? But lithium had problems. Safety was one of them. Under certain conditions, lithium-ion batteries can overheat and experience thermal runaway, creating serious fire risks. Cold temperatures can also reduce their performance. And lithium supply chains depend on mining, processing, and global resources that can be expensive and difficult to manage. These problems were not new. The industry knew about them. What many companies didn't expect was that another battery technology could eventually become good enough to compete with lithium on a large commercial scale. And that is where China entered the picture. While many American companies continued focusing heavily on lithium, Chinese researchers and manufacturers were exploring alternative battery chemistries. The surprising part is that the key ingredient behind one of these alternatives is incredibly cheap and widely available. Something ordinary enough to be sitting in a kitchen. And if this technology can deliver the safety, cold weather performance, long lifespan, and low cost being claimed, it could change the battery industry in a very big way. The real question is no longer whether lithium works. It clearly does. The question is whether lithium will remain the dominant battery technology when cheaper, safer, and more abundant alternatives begin reaching mass production. And that may be the shift the industry is only now beginning to understand. The warning signs were already there. Supply chain problems were becoming easier to see, but the profits were strong, and the industry had too much momentum. Nobody wanted to slow things down, so companies kept investing in lithium while the underlying problems continued to grow. One of the clearest examples came in 2016 with Samsung's Galaxy Note 7. When the phone launched, it received excellent reviews and quickly became one of the most popular smartphones on the market. Then, within weeks, reports started appearing that some phones were catching fire. Phones overheated on desks, in pockets, and even on airplanes. In one frightening case, a phone caught fire beside someone who was sleeping. Samsung eventually recalled every Note 7, airlines restricted the device, and the company suffered billions of dollars in losses. It was easy to blame Samsung for producing a defective phone. But the bigger problem was the battery technology itself. Lithium-ion batteries contain a flammable liquid electrolyte. If a battery becomes extremely hot, gets physically damaged, or is charged under certain unsafe conditions, that material can ignite. And once one battery cell starts overheating, the problem can spread. One cell heats the next, which heats another, creating a chain reaction throughout the battery pack. Engineers call this thermal runaway. Then there is the cold weather problem. When temperatures fall below freezing, lithium batteries become less efficient. Charging in very cold conditions can cause lithium to build up inside the battery in a way that can eventually create internal shorts and generate dangerous heat. Even when nothing goes wrong, cold weather can significantly reduce battery performance. For electric vehicle owners in places with harsh winters, that can mean losing a large amount of driving range when they need it most. Engineers have spent years trying to solve these issues. They developed advanced cooling systems, battery management software, and heaters to keep battery packs at safer temperatures. These improvements help, but they don't completely change the basic chemistry. Lithium simply doesn't perform as naturally well in extreme cold. And safety wasn't the only concern. Between 2020 and 2022, lithium prices exploded, rising several times above previous levels. Then, in 2023, prices dropped dramatically. For an industry trying to build the future of transportation and clean energy, depending on a material with such extreme price swings creates a serious challenge. Yet companies continued putting enormous amounts of money into lithium. Meanwhile, researchers in other parts of the world were asking a very different question. What if we could build a good battery without lithium at all? Surprisingly, the answer wasn't some rare futuristic material. It was something people have known about for centuries. The ingredient, hiding in plain sight. Long before lithium became the star of the battery industry, scientists were studying another element that behaves in many ways like lithium. It's located directly below lithium on the periodic table. That element is sodium, and you probably know sodium from its most familiar form, table salt. Sodium is incredibly abundant, including in seawater, which means its supply is far less limited than lithium. Scientists were experimenting with sodium-based batteries as far back as the 1960s. In 1966, Ford developed an early rechargeable sodium battery. The technology was interesting, but it had one major drawback. It needed to operate at roughly 300 degrees Celsius. That's extremely hot, far too hot for an ordinary car. So the technology remained mostly a laboratory curiosity. For decades, lithium continued to dominate because it offered better performance and was much easier to use in practical applications. But technology changes. As lithium supply chains became more complicated, prices became volatile, safety concerns remained, and cold weather performance became a bigger issue. Researchers started taking another look at sodium. The question was simple: could modern engineering finally make sodium batteries practical? And that question eventually led to one of the most important developments in the battery industry, one that could give the world a serious alternative to lithium. In 1972, scientist M. Stanley Whittingham made a breakthrough that dramatically changed the future of batteries. he discovered how to make lithium batteries work at normal room temperature. That gave lithium a huge advantage over sodium. When Sony began selling lithium-ion batteries, commercially in 1991, lithium quickly became the industry favorite. Over the next 30 years, more than $1 trillion was invested worldwide in lithium research, mining, and manufacturing. Sodium, meanwhile, was largely forgotten. It wasn't necessarily because scientists had proven sodium was worse. The problem was that lithium already worked, and companies had little reason to spend billions developing an alternative. But sodium had one major technical problem. Sodium atoms are about 35% larger than lithium atoms. In a rechargeable battery, these atoms have to move into and out of a storage material thousands of times without destroying its structure. Lithium works extremely well with graphite, the carbon material commonly found in pencil leads. Lithium ions can move between graphite's layers without seriously damaging them. Sodium is much larger. When sodium tries to enter graphite, it can damage the structure. After repeated charging and discharging, the material begins to break down, causing the battery to lose performance. So, sodium wasn't the problem. The problem was finding the right material to store it. For decades, this challenge kept sodium batteries from becoming a serious competitor to lithium. American companies had little motivation to take the risk because lithium was already profitable and widely established. But around the year 2000, a small research team in Canada discovered something that could change the situation. They were experimenting with a material called hard carbon. Hard carbon can be made by heating plant waste and other organic materials to extremely high temperatures without oxygen. Unlike graphite, which has neat layers, hard carbon has a much more irregular structure filled with tiny gaps and pockets. And those messy spaces turned out to be perfect for sodium. Because sodium atoms are larger, they don't fit comfortably between graphite's layers. But the irregular structure of hard carbon gives them room to move in and out without destroying the material. That meant sodium could potentially be charged and discharged thousands of times while maintaining the battery's structure. A problem that had challenged researchers for decades suddenly had a possible solution. The answer wasn't a new element or an expensive material. It was simply a different type of carbon. But there was still a serious problem. Hard carbon absorbs moisture very easily. Unfortunately, even small amounts of water inside a battery can react with its chemicals, create unwanted gases, and damage the cell. In a small laboratory experiment, keeping the material dry is possible. But producing millions of batteries for electric vehicles or large power storage systems is much harder. A factory has to control moisture extremely carefully and ensure every battery is manufactured consistently. The risk was simply too high, and solving the problem required far more money and engineering than most universities or small companies could provide. So the discovery sat largely unused for years. Researchers continued publishing studies. Japanese companies ran small experiments, and European laboratories kept investigating the technology. Everyone knew the science was interesting, but knowing something can work in a laboratory is very different from proving it can work in a giant factory. Someone needed to take that discovery, invest heavily in it, solve the manufacturing challenges, and turn sodium batteries into a practical commercial product. And eventually, a company in China decided to take that risk. The technology had enormous potential, but there was one major problem. Nobody wanted to spend the billions of dollars needed to turn it into a real product. The research existed. Scientists understood the opportunity. But research papers don't build factories, and potential doesn't put batteries into electric cars. What the industry needed was a company with enough money, patience, and confidence to take a risk that everyone else had avoided. American companies had the money, but most chose to stay with lithium because it was already proven, profitable, and widely accepted. Then a Chinese company made a different decision. That company was CATL, or Contemporary Amperex Technology Company Limited. Based in Fujian, China, CATL became one of the world's biggest battery manufacturers. Around 2015, CATL began investing heavily in sodium-ion battery technology. The company reportedly committed around $1.5 billion over several years to solving the problems that had kept sodium batteries from becoming commercially practical. While American companies were building bigger lithium factories and making lithium batteries cheaper, CATL was investing in a technology many people still considered too difficult to manufacture. The engineers began solving the problems one at a time. One major challenge was moisture. Hard carbon naturally absorbs water, and even small amounts of moisture can damage a battery. CATL worked on modifying the material's surface so it would repel water instead of absorbing it. Another challenge was the microscopic structure of hard carbon. The tiny pockets inside the material needed to be carefully controlled. If they were too small, they couldn't store enough sodium. If they were too large, valuable space was wasted. Getting that structure right consistently across millions of battery cells required years of research, testing, and investment. Eventually, CATL brought sodium-ion battery technology into commercial production. The reported performance was impressive. Modern sodium batteries can offer hundreds of miles of potential driving range while supporting fast charging. But one of their biggest advantages could be longevity. CATL has reported very high cycle life for its sodium-ion technology. If a battery can survive thousands of full charging cycles, charging it every day could potentially allow it to operate for many years. Then there's cold weather. This may be one of sodium's most important advantages. Lithium-ion batteries can lose a significant amount of performance in freezing temperatures. Sodium-ion technology has shown much stronger performance in extreme cold, with CATL reporting useful capacity even at temperatures around -40 degrees Celsius. For electric vehicle owners in extremely cold regions, that could be a major improvement. And then comes cost. Sodium is one of the most abundant elements on Earth, while lithium requires more complicated mining and processing. If sodium batteries can be produced efficiently at large scale, they could potentially reduce battery costs and make energy storage more affordable. That is why the technology is attracting so much attention. Why did America miss it? The surprising part is that the problems with lithium weren't hidden. Researchers had been studying lithium battery safety for years. Engineers knew about the challenges of cold weather, battery degradation, and supply chain dependence. The information was already available. What was missing was the willingness to spend enormous amounts of money developing an alternative before there was any guarantee it would succeed. Lithium already had everything going for it: massive factories, established supply chains, proven performance, and billions of dollars in investment. For many American companies, improving lithium simply looked like the safer business decision. CATL took a different approach. Instead of asking why anyone should replace lithium, it asked what could happen if another battery chemistry eventually became good enough to compete. That long-term bet helped turn sodium batteries from a laboratory experiment into a real commercial technology. And now, the battery industry is beginning to face a new question. What if the next generation of batteries doesn't need lithium at all? When a technology works well and continues making money, an entire industry can fall into a very human habit. It stops searching for something better. Change usually needs a strong reason, and that reason has to be more powerful than the comfort of staying with what already works. For years, American battery companies had plenty of reasons to explore alternatives. But instead of taking the risk, many chose the familiar path. They continued using the technology they already understood, expanded the factories they had already built, and protected the business models that were already profitable. Chinese battery companies took a different approach. They studied the same research and saw the same potential. But instead of leaving that potential inside laboratories, they were willing to invest money, time, and engineering effort to turn it into a commercial product. Now, that decision may be paying off. Sodium batteries didn't suddenly appear out of nowhere. The technology had been studied in laboratories and discussed in research papers for decades. What changed was the environment around it. Lithium became more expensive. Battery fires raised safety concerns. Supply chains became increasingly dependent on a limited number of countries. All of these problems pushed the industry to take another serious look at sodium, and the timing could be especially important for electric vehicles. For companies trying to build affordable EVs, battery cost is one of the biggest challenges. If sodium batteries can be produced significantly cheaper than lithium batteries, manufacturers could potentially build lower-cost electric cars. That could give companies using sodium technology a major advantage in price-sensitive markets. The same applies to electricity grids. As countries spend billions building renewable energy infrastructure, large battery storage systems are becoming increasingly important. If sodium batteries can offer lower costs, long lifespans, and better safety, they could become a serious option for storing solar and wind power. The biggest advantage may be that sodium is extremely abundant. The world doesn't have to search for some rare new element. One of the key ingredients is already everywhere around us. That's what makes this story so interesting. China didn't invent sodium. Scientists had been studying it for decades. What China did was invest heavily in solving the practical problems that had kept the technology from becoming commercially useful. The lithium era is not over. Lithium batteries still dominate electric vehicles, smartphones, laptops, and energy storage. But for the first time in decades, the world has a serious alternative. And that changes the competition. The massive battery deals being announced around sodium technology are more than simple business contracts. They suggest that the global battery industry may be entering a new phase, one where lithium is no longer the only serious option. The center of that new competition may not be where many people expected. China has already invested heavily in sodium research, manufacturing, and supply chains, while American companies are now working to close the gap. The real question is what happens next. Will sodium batteries become a major part of the global EV and energy storage market? Or will lithium remain dominant as manufacturers continue improving its technology? Either way, the battery race has changed. And perhaps the most surprising part of the entire story is that one of the strongest alternatives to lithium was hiding in plain sight all along. So here's the question. If a sodium-powered electric car were significantly cheaper than a lithium-powered one and performed much better in winter, would you buy it? Let me know what you think in the comments. And if you enjoyed this story, don't forget to like the video, subscribe to the channel, and turn on notifications so you don't miss the next one.